Hello everyone, I hope this finds you well. Today we're starting Chapter 2 in our option, and we're going to talk briefly about the fundamental theorem of calculus. You've all learned this already, but let's just kind of go through and review it. So, there's two versions of the fundamental theorem of calculus, and one of them says that for a continuous function f of x on the interval, the closed interval a to b, that the derivative with respect to x of the integral from a to x of f of t dt equals f of x. And the second part says for any function g of x such that g prime of x equals f of x, or in other words, g is the antiderivative of f, that you can evaluate the definite integral from a to b of f of x dx by simply evaluating g of b minus g of a. Alright, so this has many applications, and we're going to talk about how we can use this to help us do some evaluations. So let's just go right to some examples. Find the derivative of the integral from negative pi to x of cosine of t dt. Well, what the novice student would do would think, okay, first, let me calculate this. Let me just deal with the integral, and then I'll take the derivative of that answer. So let's see what happens when we do that. So the antiderivative of cosine of t dt is going to be sine. And we're evaluating this from negative pi to x. So then we plug in the x and we get sine of x minus, and then we plug in negative pi, sine of negative pi. And so we get sine of x minus a constant. Now in this case it happens to be 0, but we just get sine of x. Okay, so we've taken care of the integral. Now we want to take the derivative with respect to x of that, and that's just going to equal the cosine of x. And even if this constant was something other than 0, the derivative of that constant will be 0. So it's always just going to be cosine of x, no matter what this value is down here. Okay, but the fundamental theorem of calculus tells us, let me switch to a different color, that the integral of this function is the antiderivative of that, and then we're going to take the derivative of that antiderivative. In essence, we're going to cancel it out, and that's just going to give us the integrand that we started with. So we don't have to do all this work. If we realize and understand what an integral of a function represents, and then taking the derivative of that antiderivative, we can simply just plug in x, and we're done. All right, let's try another one. How about let capital G of x equal the integral from 0 to x of 1 over 1 plus t squared dt. Find g prime of x. So this is really just the same problem as before, it's just worded a little differently, the notation's a little different, but we want to find the derivative of the integral. So you could do it the long way and say, well, wait a minute, what's the antiderivative of 1 over 1 plus t squared? Oh yeah, that's the arctan. And then evaluate it at x minus evaluate it at 0, and then take the derivative, but there's no need to do that. We know that the answer is going to be 1 over 1 plus x squared. And that's it. Now, what happens if, why can we do it the long way? Why do we have to do this shortcut? Because I'd rather do it the long way, it makes me more comfortable. Well, what happens if I asked you to find the derivative with respect to x from, let's say, 1 to x of sine of x squared? Oops. I want to use a different variable since I'm already using x there. So sine of t squared dt. Well, I think after a few minutes you're going to realize that there is no elementary antiderivative of sine of t squared. So you're not going to be able to get the antiderivative and then take the derivative of that. So in this case, we know the answer. The answer is just going to be sine of x squared. All right, let's look at another example. How about the derivative with respect to x of the integral from x to 1 of t squared dt? Well, this is where it's important to know the properties of integrals. So I remember that if I switch my limits of integration, so I can make this go from 1 to x, and it'll be the opposite of that, of t squared dt. And so now my answer is simply going to be negative x squared. And that's it. All right, how about this one? The integral from 1 to x squared of cosine t dt. Find dy dx. What are we going to do about this one? Now, here's where the problem lies. Right there. So let's do a substitution. What if I let u equal x squared? Then isn't du dx equal to 2x? Why do we need that? We'll see in a minute. So now y is equal to the integral from 1 to u of cosine of t dt. So now everything is in terms of u, so now we know that dy du, let me move this over here, thinking ahead, dy du is simply going to be cosine of u, using the fundamental theorem of calculus. So if you haven't figured it out by now, basically we're taking this and we're plugging it in for the variable here when we're taking the derivative of an integral. Alright, so what are we trying to find? Oh, we're trying to find dy dx. So wait a minute. Dy dx, well, that's going to equal to dy du times du dx. And so that means it's equal to the cosine of u times du dx, which is 2x. And now u was just a temporary variable, so let's go back. Since u was equal to x squared, our final answer, and I'll write the 2x first, not that it matters, it's the cosine of x squared times 2x. So, do we have to do all that work every time we run into a problem like this, where it's not just an integral from a constant, here, a constant, to x to the first power? No, it's not really that much different. What we're doing is we're still taking this and we're plugging it in for the variable, but then we have a chain rule involved, so we have to multiply that answer times the derivative of that. Alright, let's look at another one. How about the derivative with respect to x of the integral from x to x squared? Now this is different from the one before because this is not a constant. But once again, here's where the property of integrals comes into play. So what I could do is I could split this up and say, well, that's the same as doing the integral from 0 to x squared of f of t dt minus the integral from 0 to x, a picture, well, I'll draw a picture for that in a second to help you visualize this, dt. And now we can do each of these independently, and so the derivative with respect to x of the first integral, and remembering about the chain rule that I just explained in the last example, it's going to be f of x squared times the derivative of x squared, which is 2x, and then the other one is just going to be f of x. We don't know what the function is, so that's it. That's our general answer. Now, the way I split this integral up, I want you to, I'll give you a visual over here. Let's just say that they're both positive. So let's say x is here and x squared is here, and our function is there. So I guess I need to extend this a little bit. So the integral from x to x squared, well, that represents this area. And when I split it up and said 0 to x squared, well, that would be all of this minus the integral from 0 to x, which would be this amount. And so the green minus the purple would give us the red. So that works out fine. Now, what if x was a fraction? Because I guess we should consider that. Well, that would mean that when we square it, that would be a smaller number. So x would actually be bigger than x squared. Would this still work? Well, once again, there's a function f. If I want the integral from x to x squared. Now, because x is bigger, remember that it's not going to be a positive amount. Going from x squared to x would be a positive amount. But we're going from x to x squared, so that's going to be the opposite of x squared to x. So it's going to be a negative amount there. So when I split it into two integrals and I did 0 to x squared, 0 to x squared would give me, oops, I wanted green. 0 to x squared would give me this amount. And then 0 to x would be all of this. And so if I did the green minus the purple, I would get that red area, but since the purple is more than the green, green minus purple would give me a negative of that red area, which is exactly what it's supposed to be. Now you can go through, if you really want to, you can imagine what would happen if x was a negative value, and look at a picture and make sure that makes sense to you. But using properties of integrals helps you. So the main idea in all of these is knowing that when you do the integral from a constant to some function of x, actually that'd be even more general. How about I just write, well, I'll just say some function of x. When we find the derivative with respect to x of this, it's just going to equal f of x. Now, if this upper limit here is a function of x like x squared or x cubed or the square root of x or sine of x, then we're going to have to multiply by the derivative of x, which in this case is just 1, so we get f of x. But if that upper limit is more complicated, you have to remember about the chain rule. Okay, so the problem set is from section 2, chapter 2, section A, page 49, 1 through 6.